So let's look at a simple pendulum. I'm going to derive the equation for the time period of a simple pendulum. So let's say that you have a mass hanging from a point, and there is oops, sorry about that. Okay, so there's a mass hanging over here, right? The forces acting on this mass are the tension, right? So this is tension, and this is weight, right? Now this mass is oscillating because obviously of a force that is pushing it towards the equilibrium position, right? Now what is that force? So let's look at the components of weight. So there's a force that is in this direction, right? So let's say that this angle is theta, right? And then this angle will also be theta, right? So this is W cosine theta, and this is W sine theta. So now this W sine theta is the restoring force that is pushing it back to its equilibrium position, right? Now I'm going to solve this in terms of torque. So the net torque acting on the pendulum is, we know that it's equal to, from Newton's second law, it's I alpha, right? And so the torque that is being applied on this mass around this pivot point, this force obviously goes through the pivot point. There's no torque due to this force. This force is producing a clockwise torque, so the torque due to this is minus mg sine theta times the so remember, this is the force and the distance is the length, right? So torque, remember, is F perpendicular times R, right? So F perpendicular is mg sine theta, and distance is L, and so that is equal to I times alpha. So this is just a mass around, assuming that the string is massless, rotating around this pivot point. Its moment of inertia is m times L squared, where L is the distance from the axis of rotation to the mass, so which is just the length of the pendulum. So this is times alpha, and alpha is, remember, the angular acceleration. Now the m cancels out. I'm gonna flip this equation over, and one of the l's cancel out, so you get alpha equals minus g over L sine theta. Remember, alpha is d2 theta. It's the second derivative of theta, and it's also, if you want to recall, it's d omega by dt, and omega is d theta by dt. And so now you can see that if we write alpha as d2 theta by dt squared equals minus g over L sine theta, let's compare it with this equation, right? So we have seen this equation, blue over here. So we've seen from simple harmonic motion. If you go back to the discussion on that, we saw this equation, d2 x over dt squared minus k over m x, right? And we saw that the solution for this is sines and cosines, right? But this equation does not have that form, right? This is theta and this is sine theta. But there is a property of sine, if you use that, sine theta for really small angles, or like less than 10 degrees, for just a small angle approximation, that sine theta is approximately equal to theta. And so it turns out that for small angles, a pendulum undergoes simple harmonic motion, not for large angles, but for small angles. And so if you again go back to the same argument, you look at the dimensions of this factor over here, it's just going to be a frequency squared. That's easy to see. You can see that G over L, right, has units of meters over second squared divided by meters. So this is 1 over second squared. And so this is a frequency squared, and so therefore we can write it as like minus omega squared theta. And so omega squared is square root G over L, and therefore frequency is omega over 2 pi, and that's that is equal to just get rid of that. That is equal to 1 over 2 pi times square root G over L. So this is the equation for the frequency of of a simple pendulum. And one last thing is that time period is 1 over frequency, and so it's just going to be equal to 2 pi square root L over G. And so this is the equation for the time period, and this is something you typically need in problem solving, right? How the time period is. Now remember, the interesting thing over here is that it's independent of the mass of the object that is hanging. So the mass cancels out of the equation, and so it doesn't matter how heavy the object is. It's for small angles, it's always going to go simple harmonic motion, and the time period is going to be given by this equation.